everyone. My name is Charalambos, and I'm going to be talking about some work that I've been doing. Again, which analysis kind of covered a few things about already, which is using wide set of binding systems from GAIA EDR3, and then just doing gravity, modified gravity tests on it. So I'm at Queen Mary, however, I do my research part-time. I work for a company called Ultra, where I'm a lead data scientist dealing with non-astro stuff, so finance, real estate, and so on. So I try to find time to do some science work, which is my main passion. A quick overview of what I'm going to be talking about. So just a quick general introduction to the wide binary test, GAIA, and the difference between GR and MOND and where we're at the moment. A little bit more about the wide binary test, so going from simulations to observables, and then showing some results that we got from EDR3, and then ending with a conclusion. So, as it currently stands today in the literature and so on, GR seems to be the best theory of gravity that we have today. Simply because it's been doing a good job on solar system scales and so on. However, we do get to the issue where when we get to things like flat rotation curves and CMB and so on, it does a decent job in fitting the observational data. However, it needs dark matter and dark energy to be able to do that. So, although obviously some of us don't really like this idea of dark matter and dark energy, so it's something that we just created to just put it into GR for it to work. So we've gone ahead and we tried to come up with new theories of gravity, like MOND, to try and explain these effects and so on. And in the past, there's been issues in trying to fit these modified gravity theories to, for example, the CMB. Obviously, Costas has been doing a decent job with his relativistic theories. So, what are actual white stellar binary systems? So, it's literally just two stars separated by a very wide distance, usually 1,000 AU. And these actually simulate the relationship between the center of the Milky Way galaxy to stellar objects, which are rotating around the galaxy here. And the difference about these wide binary systems, because they're on a small scale, even if there is dark matter touch, there can be negligible effect on these systems and how they orbit. And also the great thing about wide stellar binary systems is that there's many of these stellar systems within the Milky Way galaxy alone. So large sample data, very widely against the MOND regime, great statistics, gives us nice interpretation, even if dark matter exists. Again, it has no effect on these systems whatsoever. Okay? So with wide binary gravity tests, what are we actually probing? Because obviously there's other gravity tests that are out there. So where we're looking at things like constraining the ppm parameters, so looking at non-linearity or superpositions and the amount of space-time curvature and so on. You've got things like gravitational redshifts, gravitational waves, it's also another test of gravity, supermassive black hole imaging, and so on. But what do wide binaries test of gravity bring to the table? So they actually constrain the Newtonian part of the gravitational field, so the time part of the weak field metric, which becomes very complementary to all other tests of gravity, especially on the very large scales, and we can be able to constrain some of the PM parameters and constrain the equivalence principle. And also these wide binaries, what's good about them is that they're purely model independent. So whenever you do a wide binary test of gravity, you're not assuming any models or anything like that, you're literally just looking at their motion and their position, which I'll be showing later on. So, in the past, they haven't got much attention using wide binaries and stuff like that because the data just wasn't really good enough, so nothing was really precise and so on. And also, there's been like a large magnitude gap in the past, so pre-GAIA, where there's potentially a lot of wide binaries within this range. So there just hasn't been enough data. And also, wide binaries, because they have extremely long orbital periods, we have to rely on the phase space parameters. So looking at the snapshots of each part of the orbit itself to try and determine what's actually going on. Right, so talking a little bit about GAIA here. So GAIA is this great space telescope, so it's producing 3D map of the Milky Way galaxy, and it's very precise, and we can get very nice precise measurements for it. Now with GAIA, its radial velocity measurement isn't that great, but doing follow-up observations on the wide binary test by using ground-based telescopes and stuff like that will do a decent job to get us to very high accuracy. But what GAIA is actually giving us, GAIA is giving us 5 out of the 6 phase-space parameters. So it's giving us 3 of the relative velocities and 2 of the relative positions. That's including follow-up ground-based observations. So follow-up observations use spectrographs, speckles, and so on. Now, when we go ahead and do the wide binary test of gravity, we start doing these simulations, we need to take a few things into consideration. What we did was we tried to simulate around 500,000 to 1 million to up to 5 million different types of wide binary orbits. So looking at different major axes and eccentricities and so on. Now, this is how it's constructed in the Newtonian case. When we get to modified gravity theories, we can't really define things quite just simply as major axes and eccentricity. So we have to define it by these effective orbit sites, which is this out here, and a quasi eccentricity. And what we see is that these actually coincide with the usual major axes and eccentricity that we use in standard Newtonian gravity. So, and this is great because then what we can do is that when we begin our simulation, we keep everything on equal footing. So everything is starting from the same point, looking at different theories of gravity and integrating all this to see what we get. An example of what these orbits actually look like. We can see that here in the Newtonian, we're going to get a nice sort of closed orbit. When we start looking at different MOND interpolated functions, you start to see these orbits start to create these sort of rosette kind of precessing kind of orbits here. Looking at emergent gravity, TEVET, and so on. What's interesting is when you start adding the external field effect, if we start from 0 and we start increasing the external field effect, you see it starts to become more Newtonian. Okay? Now, obviously we can't just be standing there with a telescope for 100,000 years and just staring at one orbit because we can't live for that long. So, but what we can do is we can look at snapshots of these orbits. So just looking at loads of wide binaries and looking at each point of the orbit itself and then trying to look at its motion and stuff. So the way to do this, well in our case here, we've only got 4 out of the 6 phase-space parameters because the GAIA radial velocity measurements are not that good enough for what we want to do. So we studied the joint distribution of observables. So then we're looking at the projected separations. So looking at loads of binaries, just a distribution of the projected separation, and looking at the the ratio between the relative velocity scaled with the projected Newtonian velocity for that current projected separation. So giving us this V tilde parameter here. So, and which becomes very convenient because it becomes weakly dependent on what your eccentricity distribution might be. So if we're looking at the distribution of this velocity ratio and the projected sky separations, if we look into an ideal case where we know all of the masses and all of the phase-space parameters and so on, we end up getting these parameters here, and then we get a B ratio less than √2, which becomes very well known for bound binary orbits. So binary orbits or any orbital system in the Newtonian case, so it's going to be less than square root 2 for them to remain bound. Anything greater than square root 2, you start to get parabolic and hyperbolic flights and so on. Now, in reality, we don't have all of these phase-space parameters, so we've got to make do with the 5 out of 6 phase-space parameters. So that is the 3 relative velocity parameters and 2 of the spatial components, which is the projected separations.
What would be scientific advantage of using Fulton rather than Javier originally suggested? Projected velocity versus the separation relation is very clear. And what's the scientific advantage of inventing new parameters?
So,
the ratio of the two projected
well, the idea for using these 5 out of 6 phase-space components, well, what we're doing at the moment, we're only using the 4 because, again, the radial velocity measurements from GAIA is not great. We can't use it.
If there is already existing a good method, and then you should explain why you are inventing a new parameter. That's unclear.
Why am I inventing a new parameter?
Yeah.
I'm not inventing a new parameter. These are observational data. This is measurements from telescope.
So as you said, there is no real uncertainty added by using v tilde rather than the relative velocity, because the denominator, the DC of RP, has very little uncertainty because you know RP very well. So it's just another way of looking at the picture.
So I took the mass dependence.
And the radius dependence.
Maybe we should let it
Projected velocity versus radius.
Should we have that in the discussion session and let him continue to talk?
So,
Yes.
Can we wait for the discussion after the talk?
so
You can discuss longer. I don't have to talk long. I can talk less. You guys can discuss longer. You have to discuss. Okay? Don't worry. You can go over time.
I shall continue. So now, if we're looking at the observables, right? So then we're going from an orbital kind of simulations, and then if we're kind of converting this to observables, and in this case, using these sort of initial starting points, and then also looking at the observables at different ways of observing these white binaries, so different inclinations, alignment, and so on in the sky, then we start to get a distribution which looks like this. Okay? Now, this is just translating these orbital simulations to observables here. If we do these for millions of white binaries that we simulate, we start to get a scatter plot which looks like this. So then, as you can see, for these modified gravity theories that do not have an external field effect, you get quite a lot of snapshots or observables that go beyond this √2 limit. For theories that have an external field effect included, they tend to just leak over this √2 limit here. Now, no scatter plots aren't a great way of looking at things, so then we look at them at different projected separations. So looking at these histograms here. So as we can see, the top two going from 3.5 to 20,000 AU. The black here is the Newtonian prediction, so remaining to the left side of this √2 limit for bound orbit, and we get to see these theories where their peak goes beyond this √2 limit. Theories with an external field effect, their peak tends to be similar to what you see in the Newtonian case, and they just leap over this √2 limit here. So this is great because then when we start looking at our observational data, we can just initially just kind of look at the peaks at different projected separations and to see what it looks like. Okay? So there are some observational considerations. So just like I mentioned, theories without a field effect, it's very easy to kind of test them and rule them out depending on where this peak light is on the left side or the right side of this square √2 limit. Theories with an external field effect tends to become a little bit more difficult, so it relies on a great wealth of data and analysis. yeah, so looking at the mass ranges, which I'm going to show later on how we actually compute the masses, which is usually from the Manager data at EDR3, and also our ideal range for wide binary separation is usually around this range here, using these magnitudes out of these systems, because we don't get affected too much by projected projection effects and stuff like that beyond within these limits here. And by having this kind of ideal range of where we want to look at our wide binaries, we can tap into that point ranging, and we're not really affected too much by other effects. And we also get a large number of wide binaries in this range here, where we can do great statistics. Okay, there are some observational caveats which I just mentioned, so which might be, yeah, so things like velocity, absolute accuracy, contamination by unbound pairs. So there might be objects within the GAIA data set which are too faint, which might be an extra, it might be like an extra binary, it might be an extra source that's within the wide binary system itself that we're kind of sourcing from GAIA and stuff like that. And also the rate of velocity measurements, if we were to try and use the GAIA rate of velocity measurement, again, that will cause more errors. But the idea is that is to have some follow-up observations going on, where we use high-quality spectra from ground-based telescopes to look at methodicities, get nice precise masses, and so on. So now moving on to the actual results. So, so what we did, we started to clean our data. So we went to GAIA EDR3 and we started to clean our data, and we tried to clean it as much as we can. So looking at the magnitude limit of less than 17, going out to distances of 300 parsecs, and looking at the maximum projected separation of 50,000 AU in this case, and so on. And we also did things like cut out the galactic plane, because we know it's highly dense, so then all of these background sources will affect our measurements. Cut out clusters, because again, we get tidal disruptions on our wide binary systems. Move hierarchical systems, like Xavier has mentioned before. So if you've got one binary and it's matched with multiple other stars in the system, you just get rid of the whole bunch there. Okay, and also using the low quality stars cut from the Aranu paper. So stars with low visibility periods, again, we get rid of those. So the idea is that if you don't look good and you don't look like a wide binary system, you're just going to get rid of, we're just going to take it out. So to have like a nice sort of ATOF plot for what this looks like, we end up with around 73,000 wide binary systems. So you can see here we cut out the galactic plane, and we cut out some star clusters that will affect our measurements, and so after doing all of this thing. Okay, and the way we compute our masses and how we come out with formula and stuff like that, because we want to scale our transverse or projected velocity measurements with the circular Newtonian velocity for that current projected separation, we need to figure out what the masses are for these systems. And the way we do that, we use the Johnson-Cousins relation that comes from GAIA itself for the EDR3. And we use the Manager data set, and we're looking at wide binaries. Well, we're looking at this mass range in the Manager data set, and then from there we derive our equation for a mass magnitude relationship. Okay, so now getting to the EDR3 results, so looking at the distributions of what we see in the actual observational data, comparing to what we have simulated. So the red here is GAIA EDR3, and then we're looking at Newtonian prediction at different eccentricity distribution, and we're also looking at a MOND formula which was developed by Hongshen and Lanning, which is using the M&S interpolated function and so on, which they'll talk about in more detail later. So as we can see, theories with external field effects tend to have some kind of lining up with the actual GAIA data set itself. As we saw earlier on, theories without an external field effect, then it goes beyond this root 2 limit here, which goes on the right hand side. So we can kind of safely say we could sort of rule out these non-external field effect kind of theories. Okay. However, there is this issue with the data set where we start to get this long tail of sources which we're not really sure what they are. So we try to figure out what these sources, this long tail of sources might be. So we thought they might be random, just chance projected stellar systems. So a system that's in the sky that may look like a binary that are together, but they just happen to randomly just be in the sky, not being bound by the peak, but they just end up together. Okay. Now, however, it's not really a good fit because what we have to do for our random is we have to times it by 10 so we can actually physically see like where in the tail they could be. But because we have to times it by 10, and for this purpose here, you guys can see, they can't really explain this sort of tail distribution that we get. Now, we started to think about things like modeling triple binary systems, wide binary systems, so 2 bodies and some flybys. So then the way we started to model triples is the same way we modeled our 2-body, our 2-body systems, which is looking at this observable, so this velocity distribution model, and then we started looking at this velocity distribution model for the outer binary itself, so as it's orbiting around, and then we also did another one for the inner orbit, and then we stitched these two together by using a rotation matrix and then using this scaling factor, which is the photobarycenter, which is relying on the mass relationship and the luminosity relationship itself. Okay, so then that way we have everything within the sort of same coordinate system. Flybys are just conato stars that are all from the same cluster, where this cluster has dissolved and it started to kind of disperse out, and then you start to have some binaries that, you start to have some stars that have the same velocities, and so on with its member where it came from the same source. Okay, so putting all of these together, this ends up being our model, and then we try to fit this to our actual observational data. Okay, so then we ended up picking the thermal eccentricity distribution because that ended up being the best fit between the within the MOND case and the Newtonian case here. So we can see the green line here is our model, so that's binaries, triples, and flybys, and the blue line here is the triples, and the black line here is the flybys itself, and the red data is the actual observational GAIA EDR3 binary system. And you can see in both cases it starts to create a nice fit to the data itself. The only bad thing here in the MOND part is that the distribution tends to be a little bit fatter on this side here. Okay, so then if we start to look at these chi-square plots here, and we start to look at the different eccentricity distributions for each of these theories, looking at different projected separation bins. So again, looking at MOND and modeling its flybys and triples and 2-body system, and do the same thing in Newtonian. We start to see that the thermal eccentricity distribution for Newtonian and MOND tends to be the best in both theories. However, we start to get the best fit here for the Newtonian expectations, for the Newtonian model. Okay, now, however, we still have, we started to implement a few cuts here. So then what I did was I found this cool paper where this research done by these guys here, they started using this sort of lobster plot thing. And what they did was they cross-examined the GAIA data set, super wide tests, Kepler archives, and so on, to be able to distinguish between true binary systems and higher order multiple systems. So then the idea here is that in this dense region, on the 45-degree angle line, those tend to be true wide binaries because they'll have the same age, metallicity, and so on. And this kind of gives you this sort of lobster-looking kind of thing here, and the idea to try and cut out the lobster bodies. So then I use some machine learning algorithms to try and cut out this lobster body here. And then what we did was I cut off the lobster's head, some of its arms, but I was generous enough to give it some shoulders, and kept a little bit of its tail here. Okay. So and also we put some further cuts into the data. So then the Ruby, so the normalized weight unit vector, error, we kept that to less than 1.4. And then we've got this IPV fragmosity. And what this essentially is that in the GAIA data set, it just gives you the percentage of if a source is going to have a double peak. So then if you've got greater than 50% double peak, then it's going to give you a double peak, which will insinuate that it's going to be a double stellar system. So then we kept it to less than 2%, which should be just one peak, which means it should just be just one star. Okay, so now when we start looking at these chi-square plots, so looking at the fitting, so just having a root of less than 1.4, then having this IPV parameter, having that less than 2, combining the two, we start to see it brings down the chi-square, and then putting in the lobster cut. So again, that's a lobster without a head and a tail and its claws, but with some shoulders. We see that it starts to bring down the chi-square values quite a lot and giving us a much better fit. So this kind of insinuates that we've got rid of a lot of the triples systems themselves. Okay, so now again, the aim of the game here with wide binaries and doing tests of gravity is usually the data. And within the data itself, it's just trying to clean it as much as possible and to try and get rid of as many things as possible. Usually it's the triples and the higher order multiples that causes a lot of the issues, especially this high velocity tail that goes beyond this root 2 limit. So what we did here is we started looking at the detectability of our wide binary sample by looking at different instruments. So if we're looking at the green sort of scatter plot here, this is for GAIA astrometry going to greater than 10 years. And if we're looking at things like speckle imaging, this is the blue, so then again we can detect quite a lot of triple and higher order multiple binary systems, which if we go and do some speckle imaging, we can look at the triples, get rid of them from our data set, have a data set with just two stellar systems, and then continue our wide binary test of gravity. Okay, so how much time? Yeah, just half a minute. Half a minute. So just to conclude, wide binaries is a great way to test modified gravity theories because we go deep into this MOND regime. We've got a large sample of data, it's complementary to other tests of gravity, and there's negligible amount of dark matter, and even if there is dark matter, it does not affect these systems in any way. We've got this ideal range between 5 to 20,000 MU because we're not too prone to any observational caveats within this range here. We saw that the eccentricity distribution for wide binary systems agrees with the thermal, which is good because this ended up being quite the result from many papers in literature. And so in the future, what do we want? So GAIA EDR3 is going to give us more precise measurements, more data, and so on for better statistics. The work done by Hernandez and by Q and Xavier. Then they got this claim for a MOND system, but again, this all basically comes down to how we actually treat triples. So some more observational prospects that we need. So again, we need to do some sky surveys on the data that we actually have, so that possibly. Spectral imaging is pretty much the best one because that covers the largest range of mass ratios to projected separations for the order for us to be able to clean out our sample as much as possible. So yeah, so just to conclude, basically just clean the data set and just having a better model of how we model triple systems and flybys and any other contaminants that can be within the sample itself. Once we can control of these things, have a data sample where we 100% know they're two body-wide binary systems, and then we can continue our test of gravity. Thank you very much for listening.
Thank you very much, and so we shall have questions.
Okay, first of all, sorry for the interruption a while ago. Okay, there are actually so many issues, so it is not even appropriate to actually solve this with these questions in this short time. But I would like to comment on a few things. Okay, about triples. The triples is an unknown. How many triples are there is an unknown, but I think you didn't maybe read my paper. I think the key issue is one has to, calibrate the amount of triple, and then in your method you are considering white binaries more than 5 kilo AU separated. So there is no way you can calibrate the amount of triples, and observed amount of triples is very uncertain, So if you don't, and also the amount of triple depends on how you define the sample. So by choosing the triples, the amount of triples, you can get whatever the result you want. That's why one needs to consider wider range, both Newtonian regime and the MOND regime. And then triples can be calibrated using Newtonian regime. In the Newtonian regime, we know the dynamics must be Newtonian. Okay, so we can calibrate triples so that the data agrees with the Newtonian dynamics, and then we can see what happens in the MOND region. That's what actually I did. And in my case, I included all triples. But in case of Javier, he tried to remove all triples, so he has very small sample. And another important point is about eccentricity. And then you said that thermal eccentricity seems to agree well, but eccentricity is not a free parameter. I mean, eccentricity should come from observational constraints, and there already exists observational constraint that eccentricity is get larger at larger separation, and that's super thermal. And then one of your figures shows that you use super thermal, slightly super thermal eccentric distribution. You get a result. The MOND result is better agreeing. So that shows, eccentricity is really important. Okay? So I mean, it's not. Yeah. So actually, I have much more, but I don't want to use all this time.
No,
we can use this.
Well, I'm not trying to remember what the question was.
I don't think there was a question.
So for the triples, it's when we're simulating the triples. But yeah, you're right. We don't understand. We don't understand triples. We don't understand their distribution. This is just literally we're just kind of doing it with brute force and just trying to simulate as many triples as possible. So they're trying to create systems where, okay, now we're simulating triple body system, but now we're simulating 5 million triple systems, just like we did with the 2-body, but now doing it with the 3-body and then creating this sample data set. And then the idea is to try and mix the simulations for the 2 bodies that we have, mixing it with the triple system, so then it might be 50-50, it might be 45-55, and so to try and fit to the actual observational data, because the issue is this velocity table. And again, this all depends on how we model the photo barycenter, and so on. But again, this is still something that we need to understand, how triple systems work, and also how flybys work, since they make the majority of the tail itself. But yeah, it's for the thermocentricity distribution, because I know there was a paper done by, I think it was Kwan et al., where they looked at the EDR3 data set and they used their Bayesian statistics and so on, and they found that wide binary set systems agree with a thermal eccentricity distribution, which ends up being a coincidence because within our simulations and fitting into the data, we saw that models with a thermal eccentricity distribution fit into the data the best, and that was done independently without us actually knowing what we were doing.
Okay, so we shall have now the next question by Xavier.
Yes, you commented that in my results I claim a non-Newtonian signal just like Q, but it's all to do with how clean my simple lab is and did I actually manage to get rid of white by in tertiaries or not. I did show that I have 10 points in the Newtonian region, and I did show that in that Newtonian region I exactly reproduced the expectations, both in velocity versus separation and in mass versus velocity. So I think I can show that the cleaning was fairly well done. Also, in terms of a tail of the V-tailed distribution, I have absolutely no tail in the V-tailed distribution. So I think I can prove through 3 different independent constraints that the sample was properly clean. Now, regarding this high V-tailed distribution, you say, well, maybe there are flybys, no? Things that actually, when you consider along the line of sight, it must have a large velocity difference, and hence they should be considered. Now, you must be aware that these cases where the velocity difference along the line of sight is probably big, which I cut out because I consider radial velocities as well, as you don't, on the plane of the sky, will also appear in the high relative velocity on the plane of the sky, region that is shown, but will also appear in the low relative velocity on the plane of the sky. Having a high velocity along the line of sight does not imply you will have a high velocity on the plane of the sky. You can have a very high velocity along the line of sight and a very low velocity on the plane of the sky. So these big tails alert me to the fact that there is a substantial amount of contamination in the interesting bit where they're trying to discern a very small shift in the peak of the distribution, and which is going to be very hard given that you have contamination there. Now, you did not show your final V-tailed distribution after the slaughtering of the lobster. I wonder if once the lobster is dead, you still have the tail, the V-tailed tail or not? That's a concrete question.
We still get a tail after cutting the limbs of the lobster. But yeah, so we cut, well, by using the lobster cut, we still get the tail. However, we don't get much of the tail, and that's what leads to better fitting plots here. So this sample here. So then by cutting, having this lobster cut, it did a great job, and then our simulated data fitted to the observational data much better.
Okay, thank you very much. We shall move to the next